All right, in this lesson, we're going to look at volumes of rotation. So we're going to take the same idea from previous videos of slicing a three-dimensional shape up into a bunch of bread slices, calculate the area of that slice, and multiply by the thickness. What gets different here is that we have rotations instead. So similarly, we're going to slice them up into we're going to call this circles, not circles, that's not the right word I want to use. Discs or washers, and then integrate. So what's a disc? A disc is a circle with some thickness, right? So this right here is a disc, a coin. What's a washer? It's a disc with a hole in the middle. So all of our volumes of rotations are either going to be a disc or a washer. Sometimes people talk about the disc method and the washer method. They treat them separately. But I think it's useful to realize it's the same exact thing, and it's just whether or not you're cutting that hole out of the middle. So let's look at a couple examples here. So the disk example, let R be the region enclosed by the x-axis, the line x equals 1, the line x equals 2, and the curve y equals x squared. A solid is generated by rotating R about the x-axis. So we're going to take R and we're going to spin it in a circle like this. So it's going to come out of the screen, fold back around to the other side to be, well, let me erase that so we can see. Fold back around to the other side and trace out something that'll look roughly like this. And then continue back on the other side and create a full loop. So you can imagine, coming out like this, folding back in, and then on the bottom, having a circle. So kind of like a volcano shape where the top and bottom, or the top, or a mountain where the top over here is kind of sliced off. So the question is, how are we going to slice this into discs? Well, we're going to slice it vertically like this, because that's going to make a bunch of circles, because we're always y equals x squared away from the x-axis, so that's going to trace out a circle. So our area is going to equal to pi r, let me write that as a variable instead of capital, oops, pi r squared. Our thickness is dx because their slice is perpendicular to the x-axis. These are, thickness like that. And so that means when we integrate, we're going to integrate pi r squared times dx. And then if we're on the x-axis, then we have to go from x equals 1 to x equals 2. And that's just from what was given in the problem. I drew over it in the picture, but you could see it if we erased that. The problem here is we don't know, we can't integrate r dx, so we need to rewrite r as a function of x. Well, we do know that r is equal to y, because you can just look at the diagram and see that from the middle up to the, the function, that's our radius. And so, but y is also equal to x squared. So coming back over here, we integrate from 1 to 2 of pi times x squared dx. And then from this point forward, it's just a simple, straightforward integration. We get 1/4 times pi, 1/5 times pi times x to the 5th from 1 to 2. And then you can go through and, finish that calculation. If you need me to double check it, that's fine. But let's jump into our next example where we look at washers. So a washer example. Let R be the region enclosed by the line y equals x and the curve y equals x squared. What is the volume of the solid generated when R is rotated about the y-axis? So if we imagine rotating this shape, it's going to produce something that looks roughly like this. And this will come around. So it's going to be a cone, but then the inside is kind of carved out like this. So that's like, you can imagine a hole there, and then on the outside, we've got just a standard cone. So this is kind of like, if you've seen those triangular cups that they sometimes have at water coolers, it's like that, but the walls are kind of thick inside. So that's the shape that we're doing, just rotating it around. But that means that our cross section is going to be a washer, where I'm going to have a big R for the outer radius and a little r for the inner radius. And we'll talk about that, what that kind of means in a minute. But for now, we also know that we're slicing along the x-axis, or perpendicular to the x-axis, to get those shapes. So we're going to integrate dx, but now the question is, what's the area of this shape? Well, it's pi times big R squared minus pi times little r squared, right? If we had just the outer part minus the inner circle, that's what we're going to get here. And we know that we're integrating from 0 to 1 because that's where they intersect. So pi times big R squared minus pi times the inner radius squared. Now the question is, what's the outer radius? Well, it's y of this blue function. So r is equal to x, and little r is equal to x squared from the pink function. So then if we integrate from 0 to 1, pi x squared minus pi x to the 4th dx. And so what we see here is, again, slicing up our shape. First of all, you have to visualize it, imagine how this is going to be set up, and figure out how we're going to slice it to get nice discs with holes cut from the middle. Once we've got that, we can write in our dx. That tells us what we're going to integrate with respect to, because that's our thickness. Then we find our area, which if it's a disc, it's always going to be, or if it's a washer, it's always going to be pi times the outer radius squared minus pi times the inner radius squared. Looking at the diagram, we know that each of those radii are just the y values of their respective functions. So x or x squared. So then we just come back in, plug those in, and we end up with an integral here. And this is just a nice simple polynomial that I trust you can all integrate. If you need help with it though, let me know. That's the idea behind the disc/washer method. And it's the kind of introduction, and there's for sure going to be at least a few questions on the AP test that relate to this concept. So it is one to kind of get comfortable and familiar with.